In this video, we're going to look at the SARIMA model. Now, in our previous video, we looked at ARIMA. Now we're going to look at SARIMA. What we are doing is we are looking at two different data sets. We are looking at one that is unemployment and the other that is ice cream. So just a reminder, if you want to work through this with us, go to drstephpowers.github.io/BIA. And you'll see here in forecasting part 2, you'll get access to the workbook as well as the data sets. And so just a reminder, the data sets that we are working with here is in forecast 2, and there are 2 tabs in there. Ice cream is one of them. So when you import it in, of course, create access to your Google Drive, put the file into your Google Drive, and then pull it from there based on the location you have put that. So we are pulling one here where the sheet name is ice cream. We imported that in our previous video. And then we are also dealing with one that is, where did it go? That is unemployment, so it's from the same workbook, but just the different sheet. And that one is unemployment rates by month. All right, so we are doing the SARIMA model in this particular case. So we're going to do SARIMA, which is the ARIMA, which has the autoregressive, so that's the time lag, okay? And then you might have differencing, so you might be adjusting your data based on the relationship of the data points to the ones that previous. And then you might have moving average, where you are going to adjust and kind of smooth out some of the variability by taking the average over a number of periods. And that's similar to the moving average we talked about in previous videos. So we have those 3 components that we had in the ARIMA model. Now we're going to add to it the seasonality component. And the data sets that I've built here really are for the seasonality as opposed to the ARIMA part. So to do this, let's import statsmodel.api as SM. And from statsmodel.tsa.statespace.SARIMAX, import SARIMAX. Okay, so that's what you need to run this in addition to loading in your data sets. And as we did in our previous video, we're going to do the same thing. We're going to take the first 125 and we're going to use that as our training data, and we'll take the last 20 to be our testing data. So we've taken up to, if this is all in chronological order, we're saving the most recent 20 to test it. So we build this model and then it's going to forecast, we'll forecast the most current and then see how it works. All right, so let's do that. Now, in terms of the SARIMAX, you need to tell it the training data. So the training data here is just basically we have a time variable and we have our data here, which is the ice cream in kiloliters, right? So it is going to, we don't need to include in here that variable of time. It's simply going to call that period 1, 2, 3 in its build. So we're not loading in that actual time component as it's named and numbered with time, but it's going to just label them as periods. In our seasonal order, we have 4 components. The first is going to be the lag. That's the autoregressive component. So is there a delay between the time and when it impacts your data? Then we have here the second one is that differencing relationship in terms of how much the data relies on the previous number. And then here we have our moving average and whether we need to smooth across some periods. And then the last one is the number of periods for your season or your cycle. In this case, our ice cream data, we expect like sales to say peak in July and every July after that. So there is a 12-month cycle here. The lowest sales are going to be in the winter, and it's the winter every year. So we're going to have a 12-month seasonality to our data. We call the model, we fit the model, and then we predict with the model. Okay. And so it is predicting the amount of ice cream in kiloliters. To find the measurement error, we take the actual minus the predicted. So we're taking our training data minus what it just predicted. We take our training data minus what it predicted for the training model. So again, this is the data it used to actually build the model itself. So we expect it to be much more accurate than the data that wasn't included in building the model, right? This is kind of like looking at the R squared. In this case, we're using MAPE, and so if you didn't run the previous code, you do need this definition here. And so this is defining MAPE as our true values of y minus our predicted values. So actual minus predicted, and turning that into a percentage. So we have mean absolute and then a percent. And the benefit of MAPE is that we can then find it as a percentage to give us percentage accuracy. So here, when I put this in, this particular model is 88% accurate based on the data used to build it. We could adjust these different parameters here, add more lag, differencing moving average to try to increase that accuracy. And then the other piece we want, the part that really matters the most, is the accuracy of data not included in the model. And so here we're going to make an empty list called test predict. We are going to range through that 125 to 145, so at last 20 data points that were not included in the model, we withheld them. And so we're going to predict using these index values here, 125 through 145, that's the periods, and then have it predict and populate this list. When we do that, the data we get is not in a form that matches the data format for our original test data. So we're going to convert it to an array and reshape it so that we can subtract the predicted from the test and then calculate that accuracy. And we get for this particular one a 67% accuracy with data that wasn't in the particular model. To help us evaluate our Sarima model, we're going to use something called PMD ARIMA. Okay, so let's install this. And so we're going to create some visualizations that help us understand the Sarima model. And as we use this to help us adjust our hyperparameters. Okay. So let's take a look, and we're going to need a number of different packages here. Some of these we've already installed, so just to make sure it's all here together. Import warnings, if you want to turn off all the little errors and notifications so the output's a bit cleaner, that's what that is. Iterative tools, because we're going to create a loop here using that iter tools process. We talk about iter tools when we did some of our simulations videos, or we will talk about it when we get to those simulation videos. NumPy as NP, matplotlib.pyplot as PLT, pandas as PD, our standard 3 packages. The statsmodel.api as SM, we're using that statistical package for these models, and then that PMD ARIMA as PM. And then if we're calling pieces of matplotlib to amend the graph that aren't at the pyplot level, then we can call in that higher level package. All right, so what we're going to do is we're going to take and use pandas, and we're going to look at the date and time. So we're going to take this and we're going to say, okay, let's recognize that there is a date and time component to our data set. That is going to be the column that is the date. Okay, so let's format that first. And then by doing this, we can then plot where we have date as our variable here. And actually what we're going to do is we're actually going to turn off this component. We don't actually need to see these numbers, but by separating this out and labeling that this is a date time variable, we're able to do things with it later in our analysis. So we're going to define that variable as a date time component. Now we're going to plot our date on the horizontal. On the vertical is our ice cream in kiloliters. You can choose line styles, markers, formatting. So what we want to do is we want to look at this particular data set, and we know we have the seasonality component, right? We can see it here. So that's where we're doing our analysis. So Sarima is going to be warranted based on what we're seeing. And we can actually break this and use what is called seasonal decompose. So seasonal decompose from RC params This is going to allow, the seasonal decompose is from the stats model, SM. But what we're going to do is we're going to use this PyLab RCM params to do a plot like this, where we can actually take the seasonality components, break it down. Here's the trend, here's the seasons, here's the residuals, to investigate our model even further. So this PyLab RC params is just helping us set the figure layout here and the size. So that's what these first two lines are. And then this decomposition is coming from that stats model to help us break down and look at our seasonality. We're assuming an additive model, which if we go back to our discussions about the theory, we talked about additive and multiplicative models when you have the seasonality. So with an additive model, we can find our trend and then add to it the seasonality. Okay. All right, so let's plot this and let's look at this. So this is the original data here. This shows you the underlying trend over time. So when we take the seasonality out, what we do see is that there is an increase for the first 70 periods, then it starts to decline, then it goes back up. So even once we account for the seasonality, there still is some variability in the data here, which means that if we're creating a linear model, for example, as our underlying model, then how do I get back zoomed out? Don't do this. Bump something and now I can't see it. Okay. All right. So if we, so when it's creating a linear trend, it is going to have, it's going to impact its accuracy, right? Because if we create a line here that is more horizontal, maybe it goes up a tiny bit, then you can see that's why the future numbers might be less accurate than the past if we're going with kind of a small linear increase from the past data, whereas it seems to have dropped in the more recent. So maybe ice cream is just not as popular today as it was in this early period of time. The seasonality, you can see that here. When we look at our residuals after removing that seasonality, then what we're making sure is that it's random scatter, right? We shouldn't see heteroscedasticity, which is where the residuals start to get farther and farther away from the line as we go forward in time. It should be the same variability in residuals from the early periods to the later periods. I don't know. There's a bit of scatter here that matches scatter here, but there is less scatter early. So we're also making sure that there's not any other patterns that are unaccounted for. So making sure the residuals don't have another type of movement. You know, if we hadn't done the seasonality and we just did the trend, we would see that our residuals did go up and down and would have that seasonality in them that hasn't been accounted for. What we are looking for is that we have random scatter. In addition to looking at the plots here, what we can do is we can run what is called a Dickey-Fuller test. And the Dickey-Fuller test is looking at the underlying stability of the data. And as we can see here, as we just talked, right, that there really isn't much of a trend here. It's kind of flat, maybe goes up for a little bit of period of time and down. But when we look at our data, it looks like it is pretty stationary once we remove the seasonality. So to test that underlying stationality, we can use the Dickey-Fuller test. So we're going to, from statsmodels.tsa.stats tool, we're going to import add Fuller. And we'll just create a little function here to output the data from this test. You can just run this test outright, but here's a bit of a summary. And what we're looking for is that p-value when we run this. So this is going to be looking at the time series, which in this case is our ice cream in kiloliters, and it is going to be looking at lags in the data. So if we look at and compare chunks of time, so one that are 1 unit apart, ones that are 2 units apart, 3 units apart. So it's looking at different, how far apart, like looking at the spacing of kind of comparing different levels. And so we can see here what it's looking at is it's looking at lags up to 14. And what it says here is this p-value is 0.857. Well, the hypothesis is that there is stationality, that there's not, that the underlying data is pretty flat, that not a trend up or down, but the data is pretty flat. And so by having a large p-value here, more than our alpha, then we cannot detect a difference. And so it is likely that the data is stationary. So when we look at the data itself here, it doesn't look stationary, right? It looks like it's got seasonality to it, but the underlying data is not going up or down. That trend is pretty flat over that long time period. So all we really need to do is address the seasonality is what this is telling you. If our p-value is less than our alpha 0.05, then we do have a longer or a bigger trend that's happening underneath the data itself. So what we want to do is we want to use that iterative tool to help us figure out what the appropriate parameters are for our SARIMA model, right? SARIMA model has those 4 components: the autoregressive, the lag, the differencing, the moving average, and the seasonality. And so we can use that iterative tools to essentially run a simulation, run through here that SARIMAX, and look at different combinations of those hyperparameters. So what we're doing is we are going to tell it that we want to keep the 12, that seasonality of 12, because we can clearly see here that period of 12. What we want to do then is figure out what the other parameters should be. And so we can use this iterative process and we can give it a range. So you can change what you want it to consider. And the longer the range, the more different combinations it's testing. And it'll take a little longer, but you could look at different variability. So here for autoregressive, we could do 0 to 3 lags, and for differencing 1 or 2. And then for our moving average and how much we should smooth it out, we could do 3. We'll run this. We can change it in a moment. Probably forgot to install some tools packages. I tend to forget that. Yep, here we go. Get talking and forget to install packages and things don't run. So let's go and then try to run it here. So it's looping through and it's making some recommendations. We want to look at the back half here because we're looking at the one with seasonality. And so looking at our different combinations, what it is recommending, halftime it recommends that it has 0 lag, others 1. So we could go either way. It is recommending a differencing of 1. And then we can see that the runs here, it has come up with 0, 1, or 2 for the moving average. We could change this. Let's say we want to look at up to 6 months. Maybe the lag is more than a 3-month period of time. So let's just go with a couple more here. Okay. So even with more variety, more choices, what we're getting is that there really is no lag in this, that a differencing of, if you're going to have it, is 1, and then your moving average, you could have different ones depending on how much you want to smooth it out. So we can use this to change our hyperparameters and then rerun our model. So let's go with 0, 1, 3, 12. So if we go back to our original model, up here, 0, 1, 3, 12 is what we're going to do. So we're going to change this to 0, 1, 3, 12, and we'll rerun this. Okay. Calculate the error. Our accuracy before was 87.97 for the existing model it was built on. Okay, it doesn't quite like that one as much. Let's try our predicted data here. It was 67.46. But you can see how much that has gone up. Now it's 81.6. So we can use that iterative tool and simulation to help us figure out what the other parameters should be and to adjust. So we can assess this model. What is the seasonality? How much is the seasonality in terms of the number of periods? Do we have underlying stability? And then what should those different ones be based on what performs better with the model? Now, there is another type of a medium-term forecasting, and that is Facebook's Profit. Profit, the benefit of it is that it adds in not just a seasonality component, right, in terms of like our 12-month cycle or a 12-month seasonality, or let's say an 8-year business cycle type thing, but it also allows for differences on weekends and holidays. So Facebook built Profit as a medium-term forecasting method where they could then look at, well, people might post differently on evenings, on weekends, or on holidays than they might do during the week when they're working. And so they wanted a forecasting model that would take into consideration not just a season or a cycle, but that within each week there is going to be variability that they want to model. And so we'll create a later video on how to do Profit in Facebook. And so we've just kind of left this here. We'll come back to it in a future video.